we've been drawing our electric fields with something called a quiver plot. Remember, it looked kind of like this. If we have a charge plus Q, we want to draw the field, we just think about the force on a test charge, or we think about what the electric field should be based on Coulomb's law. If we're here, then we draw a vector like that, because a positive test charge would fly away. If we're here, we draw one like that. If we're here, we draw one like that, draw one like that. And as you get farther away, the field gets smaller. So we might draw it like this, farther away. And this worked pretty well. But it has a limitation, and that is that we're representing the strength of the electric field here with the length of this vector. So the magnitude information spreads out into other points of space. So if you draw it just right, it looks okay. But you can run into trouble. For instance, what if I wanted to draw the electric field right here, really close to the charge? It might look like that. Then it looks like we have a giant electric field in this whole region, but we really don't. We have a giant electric field right here. So the problem with the quiver plot is all these vectors kind of go in places that they aren't representing. It's really representing right there. So this is the limitation. So we're going to look at another way to draw electric fields, and that is with field lines. Field lines, and if I had to give them a definition, I would just say a better way to draw fields. And better is in quotes because really it depends on what you're doing. In some cases, quiver plots are great, but in other cases, actually, you'd prefer field lines. So let's look at a few field lines. The first rule of field lines is that the direction follows the field. Okay? So it's very similar to drawing the quiver plot, is you just think about a test charge. So let me erase this one, and we'll draw something a little bit more complicated to practice drawing field lines. We'll just do a positive charge here and a negative charge here. So just like with vectors, I'm going to think about what would a positive test charge do if it were sitting right here? Well, it would fly straight over there. So instead of drawing a few vectors, I just draw a line. If one were here, at first it would fly radially away, but it would eventually get sucked over to the negative charge and eventually go like that. And this one would fly at first radially away, but then the force due to the other charge would pull it in like that. And then this one would go up, and it would come down kind of like that, and up, down like that. These would fly away, never to return. Like that. The field line isn't giving you the direction, so you add little arrow hats to the field line, like that. To make it clear, the field is pointing from the positive charge to the negative charge, just like it should. And it's going to start coming in to the negative charge like that. And of course here, it's flying away. These would actually kind of go like this, like that. And away, and away. There you go. So that's how you draw field lines. Now you might say that's really no different than a quiver plot. All we've done is not break them up into individual vectors, but it is different, and the key is in the magnitude. The magnitude of the field is the density of lines. And by that, I mean the lines per unit area. Okay. And by area, I actually don't mean the area in the plane of the board. I mean the area perpendicular to the plane of the board, the area of lines going through a surface. So if you imagined a surface like this in this plane, perpendicular to the board, it'd be how many lines go through that. So to think about field lines, you definitely have to be able to visualize this in 3D. So let's go have a quick look at one in a visualization lab. So here you can see the field lines as we would draw them on the board with a positive charge and a negative charge, and the green are the field lines going between them. But really, this is a three-dimensional object. You can see that there's field lines going in all three dimensions off of the particles. And the way we're going to keep up with the field is we're going to count the number of lines per unit area, and here's that square that's showing you the area. And what you would literally do is just count how many lines are going through the square. So there you see another very important case where even though we draw things in 2D, we have to think about them in 3D. So if I now draw this little box here, you know that means this way. Lines are going through it. If I draw another box out here, same area, more or less, you know that's also in the plane of the board. We think about lines going through it. So the question is, if you have box A and box B, which one has the larger magnitude of the field? You can tell by looking, it's box A. Because A has 3 lines going through it, B has 1 line going through it. So when you look at the field lines, you can tell the magnitude just by how many lines, how close are they together. The field is very strong right around a charge. It's very weak, really far from a charge, and it's somewhere in between the 2 charges. But they have a way to represent the magnitude really only at one place. It doesn't matter about vectors pointing all different directions. So we'll be using field lines when we need them.